All right, so we said that we were going to come back and prove the theorems that we worked with on the previous lesson, and here we go. So if we have an angle that is formed by a chord and a tangent, and that is to say that an angle like, in this case, angle BAC, a chord and a tangent. If we have an angle like that, we know that it behaves like an inscribed angle, and that subtended arc is double the angle, or the angle is half of the subtended arc. Okay, so it'll work through this. What is the measure of angle BAD, and how do we know? So angle BAD has to be a right angle, and that's because this is a radius or a diameter, and it's attached to a tangent line. Anytime a radius or diameter intersects a tangent line, at the point where it intersects will form a right angle. So we have that. The measure of angle CAD, in terms of arc measurements, CAD goes like this. It is an inscribed angle, and so if I follow the inscribed angle out to its endpoints, it needs to be half of arc CD. Nothing new there. Fill in the missing angles and arcs. Okay, BAC plus CAD. So that's this angle here plus this angle here. They form the 90-degree angle. Fine. Arc AC plus arc CD is this plus this, and there's my diameter, so that forms a semicircle. Therefore, they add up to 180. So now we're going to use all of those facts that we just had there to derive what we were saying, that angle behaves like an inscribed angle and is half of its arc. All right, so first off, angle BAC plus half of CD is equal to 90. Now why is that? Well, because we just said that BAC plus CAD is 90, so if I replace CAD with half of CD, I haven't done anything different, it's just substituting. Okay, next step. CED is equal to 180, arc CD is equal to 180 minus arc AC. Why is that? Well, this equation right here. If they add up to 180, then one of those arcs has to be 180 minus the other one. All right, moving on. BAC plus half of 180 minus AC equals 90. That's taking the first two equations and combining them. I'm simply substituting this difference for arc CD. That's it. Goes in parentheses. Haven't done anything new there. All right. In this case, I'm distributing the 1/2. 1/2 times 180 is 90. 1/2 times arc AC. Now you see a 90 on both sides. Those will subtract each other out. If I add the 1/2 of arc AC to the right, then I get exactly what I was trying to prove. It's just a straight algebraic proof. Once you take the concepts from the diagram, if you use them in a strategic way, you can show that the angle formed by the tangent and the secant is equal to half of the arc that it subtends. So that's the proof of it. We're still going to use it like an inscribed angle. That hasn't changed. That's just why it works. All right, and so on to the next page. Proof number 2. Angles formed by two secants. What we said was that exterior angle is going to be half of the difference between the two arcs. We said it over and over again in the last lesson. Here's why it works. Segment AD was added to help with this derivation here. So this is not part of the angle, it's just added in to help with it. Okay. First thing, angle FAD is the angle formed by the dotted line and the secant here. That angle is equal to angle P plus angle ADB. That's because of the exterior angle theorem. So if I've got triangle PAD here and I extend it this way, the outside angle FAD, the outside angle is FAD. Yes, that outside angle is equal to the sum of the two remote interiors. And so just dot those, make it easier to see. So this angle here is equal to the sum of this one plus this one. All right, solve the above equation for P. Well, that's just subtracting ADB to the left and then just reversing it. So angle P is equal to the difference between those two angles. All right, so use that answer along with inscribed angle relationships. All right, so angle FAD, if it's talking about inscribed angle relationships, I think what we're going to get to here is that angle FAD is half of its arc, half of CD. And that angle D down here is half of AB, right? Because that's another inscribed angle that ends at AB. I think that's where this is going. All right, so in fact, FAD is half of its arc, ADB is half of its arc. So if I substitute those half arcs for the two angles in part B here, then my equation is going to read that angle P from this equation is equal to the difference between the two half arcs, or half the distance between the two arcs. And that's exactly what we have said all along, that an exterior angle formed by two secants is going to be equal to the difference between the two arcs that they subtend. Alright, last one. Angle formed by a tangent and a secant. And what we've said to this point is that it behaves the same way. You have an outside arc, you have a larger arc, you have a smaller arc, you're supposed to subtract them and take half of that. Okay, so again, a segment's been drawn, and if we are looking at angle FBD, that's this angle down here with the dot, compared to angle P and angle BDA, these two angles are interior angles on this triangle, remote interior as far as it's concerned with this exterior. So that's where that sum comes from. Solve it for P. Got that. So this is working the same way as the last one. I'm going to go get my inscribed angles now. So angle BCD, angle FBD is going to be replaced by half of its arc. We've seen that before. And angle BDA is going to be replaced by half of its arc too. That's half of AB. So let's just break that down again. Angle BDA is this angle up here. If I follow it out, it's this arc, right? So angle BDA is half of arc AB. The other one was FBD, which is this angle out here. That is a tangent and a chord that intercepts this arc here. It's a major arc, arc BCD. All right, continuing on with this. It works just like the last one. Substitute, combine your half. Okay, so this is just showing why it works. What we need to know is that anytime you have an exterior angle, you are going to subtract the two arcs and take half of that.